So the next talk is about escape analysis for Go, and it's given by Boyao.
Thanks for the introduction. Good afternoon, everyone. I'm Boyao from USTC. It's my pleasure to be here today to present our research work, MEA2, a lightweight field-sensitive escape analysis with point-2 calculation for Golang. Escape analysis is a method for determining the dynamic scope of pointers. That is, where in the program a pointer can be accessed. Escape analysis allows for optimizations such as stack allocation and scalar replacement. By performing this kind of optimizations, object allocations can be reduced, which reduces the pressure on garbage collection and improves the program's performance. For this reason, escape analysis is widely used in managed languages, such as Java, JavaScript, and PHP, and today's main focus, Go. Go is a young and popular programming language, and it has two main features: native support for high concurrency and efficient development. On the one hand, to support high concurrency, Go's execution unit, the Go routine, is designed to have a lightweight and movable stack. The stack can dynamically grow and shrink during runtime as needed. However, this increases the chances of dangling pointers in the program. On the other hand, to improve the development efficiency, Go employs a garbage collector to automatically manage memory at runtime. However, using garbage collection leads to more heap allocations and affect the program's performance. Therefore, Go proposes two pointer usage environments and introduces escape analysis to check the violation of the environments. For stack objects that violates this environment, they will be allocated on heap. However, Go's escape analysis is implemented on AST and lacks various sensitivities and points to information. This results in a more conservative algorithm with lower precision, leading to more objects being allocated on the heap and resulting in poor performance. First, Go's escape analysis is field-insensitive. In this example, we declare x with type x, and the address of I is assigned to x.p1, and while x.p2 is assigned to a global variable sync. From a field-insensitive perspective, the algorithm doesn't distinguish between objects and their fields, leading it to believe that the address of I is passed to sync via x. Resulting in the unnecessary heap allocation of I. Secondly, Go's escape analysis doesn't attempt to calculate the points to set for pointers. For example, here, we can know that PC points to C, and PD points to D, and PPD points to PD. In the last line, the value of PC is assigned to PD through dereferencing PPD. But due to the lack of points to information, Go's escape analysis assumes that PPD could point to any location, conservatively concluding that C might be referenced by an arbitrary by a heap pointer, leading to the unnecessary heap allocation of C. To understand the impact of the aforementioned shortcomings, we conduct a simple empirical analysis about memory access operations. And we found that field access and indirect memory access accounted for over 50%, with proportions of 33% and 19% respectively. This suggests that incorporating field sensitivity and point-to calculation into escape analysis offers a great opportunity to improve the precision. So we propose an improved escape analysis algorithm called MEA2. It combines type constraints to achieve field sensitivity and integrates the calculation of point-to sets. Additionally, we propose a general and configurable representation for function summaries to facilitate the inter-procedural analysis. MEA2 is designed based on GoLLVM, which takes LLVM as input and construct an escape graph based on it. After simplifying and propagating escape states in the graph, stack allocation is applied. First, we'll start by introducing the abstraction of LLVM. We characterize variables into two types, top-level variables and address-taken variables. Top-level variables include virtual registers and global variables, and address-taken variables represent objects allocated in the program. For the instructions and the statement, we focus only on 7 memory-related operations: allocation, cast, store, load, get element pointer, find nodes, and call instructions. Each variable v has an escape state, denoted as ESV. We can define a simple escape state lattice where no escape is less than escape. MEA2 requires the escape states of variables meet certain constraints. First, for each pointer p points to O, the escape state of p must be less than or equal to that of O. In the case given here, the global variable global PTR points to the local variable VA, and since the state of global variables is initialized to escape, according to the constraint, the escape state of the variable VA can only be escape. The next constraint stems from the specific requirements of Go for objects allocated within loops. If they are referenced by a pointer in the outer loop, they should be marked escape and heap allocated. The escape graph is a directed weighted graph. The nodes are characterized into two types: reference nodes, which represent top-level variables, and object nodes, which represent address-taken variables. The edges are also characterized into two types: flow edges, which use weights of 0 and -1 to represent copy and address of relationships between variables. Field edges indicate that the source node is a field of the destination node with a specific of set X. This figure shows a simple escape graph, and it conveys the following information. The object OBJ has two fields with offsets 0 and 16. Its address is assigned to A, and the value of A is assigned to B. First, we will introduce the rules for constructing the escape graph for field insensitivity. For the new instruction, assuming the object being allocated here is OI, we will add a flow edge with a weight of -1 to indicate that the address of OI is assigned to P. For the cast instruction, when P is a pointer type and Q is not, this can be considered as converting an arbitrary value into a pointer, and we perform a derive operation on P. The derive operation is used to represent unknown pointee. As shown here, the derive operation will create a virtual object node, OV, to represent the pointee of P and mark it as escape. In other cases, we treat the cast as a copy operation. Next, the rules for the load instructions are also divided into two cases. When the pointer set of P is empty and V is of pointer type, we consider that we may point to an unknown object, and thus we perform our derive operation. When the pointer set is not empty, we establish a flow edge from each pointee O to V, indicating that the value of V is assigned to O. The value of O is assigned to V. Next, we will introduce how to calculate the pointer set. Under field insensitivity, we can assume that if the address of O is assigned to P, then O belongs to P's pointer set. According to the definition of escape graph, the points to relationship can be represented in the graph by a path from O to P, where the first edge is a flow edge with a weight of -1, meaning the address of O is taken, and the rest are flow edges with a weight of 0. meaning the address of O is passed to P. As shown in this example, the left code snippet includes 3 instructions based on the rules for the new and the cast instructions. We first establish a flow edge from OBJ to V, and then create an edge from V to C. For the load instruction, we first calculate the point to set, and we can find that there is a path from OBJ to C, starting with a flow edge of weight -1, followed by a flow edge of weight 0, which means C points to OBJ. Thus, we can establish an edge from OBJ to LD according to the early rules. The rules for store instructions are similar. When the point set of P is empty, we conservatively consider that the value of V is passed to our heap object. Otherwise, we can consider that there is an assignment from V to the object pointed to by P. Next, for the find instruction and get element pointer instructions, we will just consider them as assignment. Next, in the context of field sensitivity, we will need to introduce the concept of type compatibility first. We see that variables v1 and v2 are type compatible if they have the same underlying data layout. For example, although v1 and v2 have different types, they have the same size for each underlying data field and can be converted to each other. Thus, we say they are type compatible. And then we can define an assign operation to handle the assignment between two typed variables. If they are type compatible, corresponding flow edges will be established between each of their respective fields. And otherwise, we consider that they cannot be safely assigned, leading to our conservative approach. Next, we will introduce the calculation of the points to set for field sensitivity. We introduce the constraints of type compatibility to refine the points to information. Consider the following example. OBJ is of type T1, and C obtains the address of OBJ through V. At this point, there are three object nodes whose address equal to the value of C. OBJ, OBJ.0, and OBJ.0.0. Among these, OBJ.0.0 is compatible with the I8 star type, and therefore C points to the OBJ.0.0. And we can finally add an edge from OBJ.0.0 to LD. In the context of field sensitivity, the rules for load and stores are modified as follows. The calculation of point to set and assignment or assign operation is adjusted. Finally, we will talk about the rules for get element pointer instructions. When the point to set of P is not empty, for each object O that P points to, we will create a new object node O.x and add a corresponding field edge to represent that O.x is the field at offset x of O. Additionally, we add a flow edge from O.x to F with a weight of -1. And as for inter-procedural analysis, MEA2 adopts a function summary-based approach. Function summaries are records of data flow relationships between parameters, return values, and heap objects. Each function summary is a combination of flows. The design of flow is as follows. It consists of a source access path and a destination access path. Each flow represents an assignment between the node accessed from the source access path and those accessed from the destination access path. For example, here is a function called JCWriteBarrier, which performs a store operation from parameter Q to P. Its corresponding escape graph is shown on the right. We can see that there is an edge from Q to star P, which is the content that a flow needs to record. First, it records the access path from star P to P, and indicating how this node is accessed through P. Secondly, it records the access path for Q as the source access path. Based on the summary, we can define the construction rules for code instruction. For a code instruction, we first retrieve the summary of the code function. For each flow in the summary, we identify the nodes accessed by the access paths and perform assign operations between the source node and the destination node. For example, in the following case, the full function calls GC barrier. Before analyzing the code statement, its escape graph looks like this. Based on the summary of function, we can first locate the source operand V accessed by the source access path, and then identify the destination operand OBJ based on the destination access path. And finally, we will add an assigned operation between them. And finally, we evaluate MEA2 on dataset consists of 12 widely used open source Go projects. First, we attempt to evaluate the effectiveness of MEA2. We compiled the source code in the projects using GoEA, which means Go's escape analysis, GLEA, which means GoLLVM's escape analysis, MEA2, that's ours, and the field-insensitive version of MEA2, namely MEA2 FI, and counted the number of heap allocation sites in the generated code. The first chart below here shows the total number of heap allocation sites for each project. And the second chart shows the proportion of heap allocation sites reduced by MEA2 compared to other algorithms. We can see that MEA2 results in the fewest number of heap allocation sites, and compared to GLEA, heap allocation size is reduced by 7.39%, and compared to GoEA, heap allocation size reduced by 6.83% in average. Secondly, we conducted dynamic tests to evaluate whether programs compiled with MEA2 could achieve performance improvement. Since MEA2 is implemented based on GoLLVM, we use GLEA as baseline. We selected 46 memory-bounded unit tests from the projects as test sets, and collected runtime statistics by compiling and running them. The results are shown in the graph. On average, programs compiled with MEA2 reduced execution times by 2.04%, garbage collection frequency by 29.29%, maximum heap size by 15.5%, and total heap memory allocated by 16.3%. Okay, that's all. Thanks for your time.
Thank you. Any questions?
Sorry. Thanks for your talk. That's very great. So I have a question about your motivations or the difference between the traditional escape analysis on C or C++. I mean, so actually your work is conducted over the LLVM framework. So my question is, so what's what's the difference between the traditional escape analysis on C and C++ and your analysis on the Go program languages?
I'm sorry, due to the time limitation, I have hide this page.
Okay.
There are many existing works on Java about escape analysis. Okay. But I think the difference is Go offers a different memory access paradigm differ from Java, because in Java every field is a reference, and in Go he's like C or C++, and his field can be a subject of the object of field can be a subobject, and any field can be referenced. This makes are different from Java. And as for C++, because there are not escape analysis work about C and C++, because they are not garbage collected.
Okay, thank you for answering. So I have a follow-up question. So can you just directly use your current framework to analyze the C++ code? I mean, there could be some kinds of similar features like the fields or the pointers, the objects in C++. So
actually, because our work is based on GoLLVM, it is based on LLVM. So I think actually it's the same.
Okay.
No matter C, C++, or Go.
Okay, thank you.
I have a question also. So how does this points-to-analysis relate to more traditional points-to-analysis techniques like subset-based Anderson-style analysis?
Compared to traditional points-to-analysis, this is faster because escape analysis doesn't require to compute the point-to set of global variables. They just compute some point-to set of local pointers. So there are many conservative handle of the in my algorithm, like here the sorry. Oh, sorry. Like the derive operation I have just talked about for any object that may be allocated outside the function. I will just use our virtual object, and this will simplify the point-to-set computation.
Thank you. Thank the speaker again.